Ready? Okay. Everyone, welcome back after the midterm. I guess it was a fun experience for everyone, I'm sure. A few notes about the midterm. Actually, a couple of announcements to start off with. First of all, problem set 3 is going to be out on Monday. The reason for that is that we pushed the deadline for the project proposal back, and so that also pushed the milestone back, and then that was going to be right next to the project, the PS3 deadline, so we just pushed it all back by a day. It'll be out on Monday. It'll be much like the last homeworks have been, so no surprises there. The midterm, we are making every effort to grade it by as soon as we can. And there was a note though on Piazza mentioning that the drop deadline for the course, I guess, is on next Monday. So if you are genuinely considering dropping the course depending on your score in the midterm, first of all, come talk to us, because you probably shouldn't do that if you've done all this work already. But if you are considering that and really want to know your midterm grade by well in advance of Monday, send us a note on Piazza, a private note, and we will send you your score ideally by Friday. We're hoping to have them all graded by Friday, so we can also send things like the mean and a standard deviation. So you'll have some sense of not only what your score was, but where you lie in regards to other students. But please only do that if you in fact do really need it, just because sending out lots of private notes. So we'll have them all graded, but sending out lots of private notes is just kind of not the best use of time. And you'll get them back on Monday anyway, so you'll get it back soon enough. The last thing, and I guess he's not here right now. Oh, there he is. So the last thing is that, as you might have noticed from class on midterm, we have a new TA in the course. So Adam has transitioned from a student to a TA, which I guess means he doesn't have to take the midterm, right? So everyone's probably jealous of him. But he's also going to help grade papers, the homework stuff a lot faster. I think there has been a little bit longer delay than we hope. It's actually a very big class for the number of TAs we have and the sort of number of assignments and length of grading assignments. So we're going to try to get it back faster based upon this stuff, but Adam is now a TA, so he will also be holding some office hours in the future, and we'll decide when that is. 4 office hours actually for Adam to be holding. Can the people that cannot make any of the current office hours stay for a few minutes after class? I've had a few of those comments, and just if you're in that boat, just stay after class and let us know what times you can and can't make. Hopefully we can find a time very quickly that does not click with anyone, because it would be a shame if we picked another time and still you couldn't make it to the office hours. So we're going to hold 1 more set of office hours per week, but stay after class if you cannot make any of the current ones. That's after class right now, after class on Monday, and then also on Tuesdays and Thursdays at the times. I forget actually the exact times, but they're on the website. All right, I think that was everything sort of logistically I wanted to mention. Were there any other questions? Yeah. The milestone is going to be 1 class day later than it was originally. The deadline is now updated on the schedule. So if you go to the lectures page, it will have the correct due date on the lectures page. That is with the PS3 and the milestone pushed back a little bit. The final report will not change, but we don't actually quite know when that's going to be yet, because we don't want to find out when our final time is yet. They haven't all been scheduled yet. So we're still waiting on that. We will have the poster session during the final time. There's no final, but we will make probably the final write-up due a few days after that, essentially what it boils down to. But they should all be up to date other than the final project deadline, essentially. I guess the other thing is we will, now that the midterm's over and we can quiet down a little bit, we will release some information soon about the presentations you give and the posters for the final project. They're both kind of standard. The presentations are very, very short, like just really an advertisement for your poster, and then the posters are kind of the standard poster you probably have in a lot of classes for final projects. Any other questions? All right, and I guess we're also going to release on Piazza, for those that want it, standard deviations and means for the homeworks, just so people do know where they stand. Everything's graded on a curve, and it's a graduate course, so they're graded accordingly, as most graduate courses are, which is to say sort of pretty leniently, I guess, as compared to a lot of classes, in terms of the actual grade average. but you'll at least get a sense of where you guys stand relative to the rest of the class. All right, well, then let's jump into the rest of the class today, which is going to be about reinforcement learning. This will actually be kind of one of the last non-application topics, I guess, of the course. Kind of one of the last core AI topics. After this, we're going to transition to lectures on vision, on scheduling, on robotics, and natural language processing. And so essentially, this was originally going to be before the midterm, and we kind of break at that point. But now we have one lecture after the midterm on kind of what's considered more the core algorithmic side of AI. And this also ties in very closely with the lecture last time on Markov decision processes. So what is reinforcement learning? This lecture is going to first briefly review MDPs. It was right before the midterm, so maybe not everyone was quite focusing on that and that lecture. What are MDPs, and more importantly, what are the challenges that reinforcement learning faces that they're trying to overcome above and beyond standard MDPs? Then I'm going to talk about two classes of methods people use that go under this framework of reinforcement learning. And these are model-based and model-free approaches. We're actually going to spend most of the time talking about model-free approaches, and there are going to be two. There are going to be approaches based on temporal differences, which are called TD algorithms, and then approaches based on policy search. And finally, we'll talk a little bit about exploration and exploitation. Most of these will be fairly brief, but we will spend some time in detail talking about a couple algorithms that are model-free, that are kind of what people think about as the standard reinforcement learning algorithms. All right, so let's jump right in. The standard domain that we sort of considered in an MDP framework is one of an agent acting in an environment, right? And so the MDP framework says we're an agent. We can take actions that affect where we are in the environment, and what we observe then is a state and a reward from our action, right? And this process repeats. Take another action, observe another state and reward, etc. This is exactly the MDP framework, but it's helpful to think of it just in terms of this agent making choices and seeing what happens from those choices. Because that also will get to a little bit of difference between MDPs and reinforcement learning as we typically think about it. But let me give an example first. So this is a robot from one of the labs at MIT. It's worked by Russ Tedrick and others at MIT. And this robot here, there's actually a lot of things going on here. This robot's what's called a passive dynamic robot, in that actually if you put it on a treadmill like that, it can walk just by sort of its mechanics will make it walk downhill. When you put it on flat ground, though, it has some actuators as well. But when you put it on flat ground, it no longer knows how to walk, right? It will sort of naturally move downhill if it's on an inclined surface, but here it doesn't really know what to do. So what they've done here is they're using a reinforcement learning method to, over time, encourage the robot to walk better. There's no sort of physical simulator in the system. There's no notion of what really is good other than moving forward and kind of having these cyclic patterns. That's all it tells it is, moving forward is good and cyclic patterns are good. But from that, what the robot's able to do is take actions in terms of moving its actuators, moving its motors, see what happens from that, and learn after about 20 minutes of real experience on the actual robotic platform. It learns how to do a fairly nice walk here. Unfortunately, some of this is kind of blurry there, but it's learned after a very short time period, just from seeing, taking actions and seeing what it does. It's learned how to walk forward, much the way it walks sort of downhill, just from its own dynamics. So how does that all work? Well, we are here operating in the framework of a Markov decision process, as we were before. And just to remind everyone, an MDP consists of, formally, I'm going to write it as a tuple, which has 4 elements. The first one is a set of states. And you should think of these, at least for this class, as being discrete. So these are a set of states essentially numbered 1 to k, where k is the number of states. Or maybe n would be the number of states, however you want to denote that. There also will be a set of actions. And these are also, for our case, going to be discrete. these can both be continuous in the general definition, but it's much harder to apply a lot of these methods when S and A are continuous. So we're going to consider the case of discrete states and discrete actions, at least for this course, and at least maybe up until a couple slides toward the end. Then there's also a transition matrix. And I'm writing this as a function that takes a state, an action, another state, and maps between 0 and 1. And what that encodes is this quantity here, S for some, or T for some S, some A, and some S prime. That corresponds to the probability of transitioning to state S prime if you're in state S and you take action A. This is just a review from last lecture, but just sort of putting these all on one slide here. And finally, R is a mapping from states to real numbers. And this is a reward. And the goal of most RL algorithms, or the most really an MDP algorithm in general, is to maximize the sum of rewards that you see. Where you can define it either as a discounted sum of rewards going to infinity, as the average sum of rewards going, averaged, going to infinity, but averaged over that time, or just to a finite horizon. But the goal for any MDP really is to maximize the sum of rewards by taking actions subject to these dynamics here. Now, what is new to RL, reinforcement learning? I should also say that some people would classify solving an MDP as also being a subset of reinforcement learning. So if you read the book on reinforcement learning, they will include MDPs and value iteration and policy iteration as chapters there. But the more common usage here is that RL is MDPs where you don't have all the information. In particular, typically, you consider either an MDP where we don't know the transitions or the rewards. All we can do, rather, is just act in this environment and see what happens. That's the typical setting for reinforcement learning. Now, that is not always the case. So some people use the term RL to mean other things. And one thing they often mean instead is RL is Markov decision processes where maybe we do know them, but we still can't enumerate all these things explicitly. They're just too big to actually enumerate. And so we have to use other techniques to try to solve these things approximately. I think there is some debate as to whether or not that is really RL. But certainly sometimes people apply similar algorithms in this case as they do in the case where we don't know T or R. And so, in fact, they end up being very similar methods that you would use. But in general, we're going to consider the case typically where RL is MDPs where you don't know transitions or rewards. All you can do is act on the MDP and see what happens. All right, so in this setting now, there are a few things we might want to do. These things are both, we again covered last time, as just a review here. But the question of RL is how can we do these things when we actually don't know the transitions or the rewards? Because for now, we're going to assume that we do know them. So just more definitions here. A policy is a mapping from states to actions, right? So a policy says I'm in some state, what action do I take? And a very common thing you would want to do for really solving an MDP is to, for example, determine the value of a policy. So remember, the value is defined as the value is the expected sum of rewards when you start in some state and you execute actions according to that policy. That part, I guess, isn't really written here, but it's the expected sum of rewards when you start in some state and you act according to that policy. Now, the value functions here, it's important to think of these in the correct way. These are, you should think of these as just sort of tables of what value exists for every single state in the system. Remember, these are discrete quantities here. So think of this as a big vector that just says what's the value for this state, what's the value for this state, etc. When you have a fixed policy, you can write this value function for a fixed policy in this form here. This is a Bellman equation, which we also covered last time. But basically it says we're going to have the reward that we had from that state plus the sum over all possible next states, the probability of ending up in that next state times the value under this policy of that next state. Okay? And it turns out you can actually compute this thing by just repeating this iteration here. Or actually, it's even simpler. These are all linear functions here. So this whole thing here is a linear function of all these values because they appear over here and over here. So you can actually compute this by just solving a great big linear system. But this iteration here actually is not that bad an idea. And it actually turns out we're going to do something very similar to this in the case where we don't know the true dynamics. Something else we might want to do is actually not to determine the value of a fixed policy, but actually the value of the optimal policy. Oops, I wrote that wrong. That was a typo there. This is the right one. Anyway, I think I swapped these two somehow. Anyway, the value, so don't look at this one. The value of the optimal policy is equal to the reward plus actually what should be here is the max over A. So the best action you can take times the probability of ending up in the next state from that action and the optimal value of being in the next state. Let me just write it here. So what it actually says is V star of S equals R of S plus gamma times the max over A of, the camera cuts off here, so I'll write the next line. Sum overall S prime in S, T, S, A, S prime, V star, S prime. Okay? So that is the relationship for the optimal value function. And what's very nice here is we could actually compute this process here. Man, there's another one here. I think I swapped that. So that should be V star there. We can compute this thing here by essentially taking this equation and iterating it. So we have our estimate of the optimal value function. And I'm going to use, throughout this lecture, I'm going to use hat to denote something which is going to try to be an estimate of that function, but which is not exactly that function. So this equation, or rather this one, defines the actual optimal value function. But this one sort of says how we get to it, which is we take this quantity here and we assign it to be this thing. This is a procedure that we covered last time. It's called value iteration. And it will actually converge to the optimal value function. That's the value function of the best policy for that MDP. And if we want to actually recover the optimal policy, then the optimal policy is just the one that actually maximizes this thing. So we look at the state we're in. We take the max over all A of this thing on the right-hand side here. That maximizing action is just the optimal policy. So it should all be a review, but kind of boiling down these two things as things that we want to do in MDPs. The question now, though, is how do we do this when these two things are unknown? If dynamics are unknown and the reward is unknown, well, clearly those things are used very heavily here, right? Here's the dynamics. Here's the reward. How do we actually compute this if they aren't known? And that's going to be the topic of reinforcement learning. Now, there are typically two ways of doing this, as I mentioned. There's the model-based approach and what are called model-free approaches. The model-based approach, though, I think is actually quite a bit conceptually simpler, kind of the thing you would think to do first. And interestingly, it actually performs very well and a lot better than these methods in a lot of cases. Let's talk about what this means. Well, this is sort of the obvious thing. We don't have knowledge of the MDP, but conceptually, it's not that hard, right? It's just probabilities. Probability of being in state S prime if you're starting in state S and take action A. So let's imagine we have a lot of data from this system. That's what we can get from our interaction, right? We can look, see that we're in some state S, take some action A, end up in some new state S prime, and we keep doing that. So we do have a lot of data from the system. And I'm going to write this as a bunch of samples. Si, Ri, Ai, and S prime I. Right, where these essentially are just samples of, we start in some state S, take observe reward R, take action A, and then it wind up in this next state S prime. Okay, and these can be these could either be sort of a single chain of experience. We could sort of end up in the next state, call that S prime, then call it S for the next sample, etc. Or they can be just really generated however we want to. We can put ourselves in a new state every time in the MDP if we can do that. Maybe we can't do that, but if we could do that, we can put ourselves there. And we just clicked a bunch of these things. OK, now, what we do is just the obvious sort of counting to estimate probabilities. Right? So for example, we can form an we don't know t, right? But we can form an estimate of t by just looking at how many times were we in state S, how many times were we in state S? Did we take action A and end up in state S prime? All right, and this notation here just says, from all our samples, this quantity here will be a 1 if for this I, Si equals S, Ai equals A, and S prime I equals S, where these are just the sort of the definitions here, or rather the inputs of this function here, divided by the number of times we were in state S and took action A. Right, so this is just really counting, right? We want to know what's the probability of transitioning to some state, given that we're in state S and we take action A. We just count in all experience how many times did we actually get to state S prime from taking that action in that state. So it's and the reward's similar. We basically just take all the times we're in that state, multiplied by the reward, and divide by the number of times we're in that state. That's sort of the average reward for being in that state. And this is kind of learning in some sense. It actually definitely is learning. But it's also kind of the easiest possible learning, right? We're just making counts here. It's just counting and looking at probabilities from counting. So now we do this, and we solve the MDP with these estimates. It turns out what you can show is that this will actually, so I should have had this written there? Yeah, so I have this on the next slide. But what you can show is that this actually will converge to the true MDP and the true reward if you have enough samples from enough different state and action pairs. And I'm being very vague here when I say given enough samples, because actually getting those samples is actually often the hardest part of reinforcement learning. How do you actually direct yourself to get those samples? That's a very hard question, which we'll get to much later in the lecture. But for now, just assume that we have some way of generating, enough, whatever that means, enough samples from each state and action. We're going to say that enough times, and so we get an estimate of all the transitions, all the rewards, and we just solve our empirical MDP. Right? So it's sort of the obvious thing to do. You don't know the MDP, you just estimate it. It's all discrete, so these are all just a finite number of parameters here. And you can just go ahead and estimate it and then solve it. And despite the fact that it's very simple, there actually are some strong advantages here. The biggest advantage is that it's actually, this process is using the data quite efficiently, because you're using all your past history to build a model of your system. Right? You're not throwing out any data or sort of making small adjustments. You're just using all your data and seeing what that will actually produce in terms of the model. Now on the downside, you are still here. We kind of got rid of some problems, but only kind of in a kind of trivial way. Right? Because we're saying, OK, we don't know the MDP. If it's really possible to estimate it well enough just from samples, you kind of do know the MDP, right? It's just that, yeah, maybe you didn't know it at first, but it's not that hard to learn in some sense. And so this is also kind of disappointing, because it doesn't quite get to the core of the problem here, where we somehow feel like we should be able to solve problems that you can't solve with an MDP here. And here we're just using a really simple algorithm to learn an MDP and then solve the model. So it's kind of unsatisfying. This is not really a disadvantage, but I guess it's sad for us if we don't feel like we're doing a really impressive algorithm here. Also, if for example, the state space is too large, to represent, this clearly won't work, right? Because if MDP, if the state is too big for an MDP, well, this is just forming the MDP, so that's not going to work. But as I said, despite this, I think kind of sadly maybe, a lot of initial successes in RL, which using other approaches, using model-free approaches, were actually shown to be kind of worse than this simple model-based approach. Not all of the success stories, but some of their sort of main ones were shown to be actually quite a bit worse. So this is a figure from Chris Atkinson, who's a faculty member in robotics here. It's almost 20 years old now. And it was published, again, when some of this, the hype was very big on reinforcement learning because they were solving a lot of these problems. This is on a problem called a called an Acrobat. An Acrobat is a double pendulum that is actuated only at the elbow. So it looks something like this. I'll actually show this again when we do robotics as an example of a dynamic robot. But it's kind of like this. It's a 2-link robot arm where this is fixed to some ceiling there, and then or some attachment there. And the goal is to try to swing this thing up, ideally to balance up at the top, but maybe just swing it up above a given amount. The key point being that you can't actuate this joint; you can only actuate this one. So you basically have, not enough inputs to really control your system entirely. You have to kind of, use your mass and kind of swing it up to balance on top. Not like I was doing there, because I actually can't control my shoulder. This is the problem, and this problem had some successes as an initial case for RL. RL was able to do a fairly good job of learning how to, from knowing nothing about the system to learning how to swing up and at least, get the Acrobat above some level. What was shown in this paper was that actually those methods that RL was using, they're this line here. And this dotted line here is if you just build an MDP of the system, exactly what we talked about before, or more or less as we talked about it before, and just solve that. And this is cost here, so lower is better here. And clearly, and it's also a log scale even. So these things are very far apart in terms of their values. And I wouldn't want to take this method in this case. I'd want to go with this one. So I think a lot of the original success has to be sort of tempered a little bit because it was shown that in a lot of cases, this model-based method, which is just the sort of the simple thing anyone would do, right? If you don't know it, just learn it and then optimize everything. That actually works pretty well, or can work pretty well. So having started on that, yes?
So was he using discrete MDP?
Yeah, so he discretized the state here and then solved it, giving a discretized, for a discretized version of this. Yeah.
So it seems like a very continuous system.
It isn't actually that hard, right? Essentially, there are 4 variables of interest here. There's the 2 angles here, and then there are velocities. And the input is just the amount of torque you apply to the other joint. And so you just chop them up into bins. We're not going to really talk about discretization here. Maybe we'll talk about it a little bit when we talk about robotics. But essentially, if you have some continuous space, you can approximate it by just taking sort of the cross product of all possible states and discretize and sort of chopping them up into fairly small little grid cells. It will not always work because effectively you could be in the same state but actually be in a little different true underlying state. But it actually can work fairly well in a lot of cases, especially if you sort of take into account the stochasticity of the system. This can work fine. Discretizing it can work fine. He's also done a lot of other work on sort of continuous versions of this, and that there are continuous versions, things that are similar to reinforcement learning that use a continuous sort of state space. But here, I believe, I have to check this actually to make sure, but I know you can take a discretized version of this and it works fine, and the model-based approach does work very well.
Can't you just discretize it by sampling?
Discretize it by sampling. Maybe, but the thing is that you're actually better off oftentimes taking a uniform grid. So sampling, if you have samples in the state space, right, there is no guarantee that taking any action that you have some other sample that will correspond to that. A uniform, does everybody actually understand the question? So the question is, can you just sort of pick some arbitrary points and treat those as your discrete states? You can sometimes, and you can do things that kind of work like that. The problem, though, is that if you have some sample and you take some new action you haven't seen before in that sample, what next state are you going to end up in? There's no guarantee you will end up in a good next state. The other sort of tricky part with sampling is that this quickly breaks, and I should also say discretization in general, quickly breaks down. We'll get to this a little bit in a second, but it quickly breaks down when you have many dimensions of continuous state, for example, because the number of discrete states you have, if you want to try to create all sort of cross products of your possible continuous states, that will grow exponentially in the number of dimensions you have in your original problem, and that really gets nasty quickly. So then sampling has the same effect. And also, we have bad intuitions here. So like, if you have a state space that's 10-dimensional, you take 10 million samples, you haven't even started to cover that state space. You're not even close. And so a lot of people think 10 million samples is a lot, but it's not. It's a tiny amount when you're talking about R10, right? So sampling, you gotta be careful with that. Now, having said that, there are sampling methodologies people do use, but we won't talk about those here. Anything else? So having ended on that sort of downer, let's talk about these methods now. Let's talk about how we get that really bad performance. Let's talk then about how we can, what situations this actually might work in that other things don't work in. So there are really two classes of model-free approaches I'm going to talk about in this lecture. And I'd say this is all pretty high level, even though we're going to delve into this a little bit. But this one we're not going to cover in too much detail. The first class of approaches, which are kind of the canonical reinforcement learning algorithm, are called temporal difference methods. We won't get into the name of that. It's sort of a name that stuck very well. Temporal difference, or TD. And these are things like TD, or Sarsa is another one, or Q-learning you may have heard of as another example of temporal difference methods. And what these do is, remember, our model-based approaches directly built a model of the underlying MDP from data. Right? So we didn't know the model, but they learned it. What these approaches are going to do is they are going to directly, they're not going to build a model of the MDP. Instead, they're going to directly learn the value function. Either the value function for a fixed policy or the optimal value function. Right, so remember, those are sort of the two things we want to do in MDPs. Evaluate the value of a fixed policy or of the optimal policy. And TD methods get to these two things exactly. They just do it in a way that does not require us to know the model of the MDP. The next class of methods, which are called direct policy search methods, those even go a step further and try to just directly learn the optimal policy pi star. So we know that if we know the optimal value function, we can come up with the optimal policy. But if all we want is the policy, why even bother with the value function? It will turn out this is actually a harder problem in some sense, because this is actually a non-convex problem. So we don't expect to necessarily find the single optimal value, the single optimal policy. But nonetheless, can actually be, in a lot of cases, a much sort of better, or at least more direct way of solving the problem we care about than trying to go through, this intermediate factor of the optimal value function. But you'll note in both cases, we don't ever talk about learning the model itself. We just talk about learning either the value function or the policy. And this is kind of what people typically refer to as RL. Model-based RL sometimes is, people call it model-based RL, but if you weren't in computer science, you would never call that reinforcement learning. You would call that solving an MDP that you learn from data. All right, so let's talk about the temporal difference methods. So I have the algorithm here, but let me sort of get to this a little bit by writing what I had on the previous slide, which was for a given policy. So now we're talking about policy evaluation. So we want to take a fixed policy and evaluate the value of that policy at all the states S. So one way we can do this is to repeat the following iteration. And I'll put hats on this now because this is exactly the equation on the previous slide. But the hats mean that we don't know the value function yet. It's just we're trying to estimate it. We're getting a procedure for estimating it. So this is going to be assigned to, in the previous slides, the reward of that state plus gamma times the sum over all S prime T S pi S. Can we get is the video camera going to track over here? Can we make sure it does? Okay. S prime times V S prime. V pi hat of S prime. So essentially what we do is we take our current estimate of the value function and we use that to update our estimate of the value function. And this process will, in fact, converge to the true value function. The problem, of course, though, is that we're using the model here. So what TD is TD, stands for temporal difference, is just a stochastic version of this. All right, that's all it is. What TD says is, and this is sort of the official definition because we have a policy and then some numbers here. This one's the discount factor we had before. Alpha is a little bit different. I'll show you in a second. But what TD says is, OK, look, we don't know this thing. But as we act in the MDP, we are effectively getting samples of this thing. So let's just act in the MDP. That means we're in some state. Here we're going to behave according to this policy. So we're going to take action pi. We're going to then also get a reward. I guess that actually happens before we take the action. And then we end up in some next state. We just keep doing that. Right? What TD says is, OK, let's take my current value then and just have this same equation. Almost. So I'll write it like this. R S plus this thing. But instead of some sum like this, let's just take the value of the next state we actually end up in. We know that is sampled according to these transitions here. So all we're going to do is say this is kind of like gamma plus V hat of S prime. Actually, sorry, I shouldn't say R of S because we don't know that either. This actually is little r. That's the reward we observe. All right, so does that make sense? So we're in this state. We saw the reward r, and we took action pi of S, and we ended up in the next state S prime. So all we do is just say, OK, that's the reward we saw, and that's the next state we saw. Let's just update it as if that was sort of all we could have possibly observed. The problem, though, is this actually will only work in a purely deterministic system. Is it exact? Because otherwise, there was some probability we ended up in a different state, too. So if you just do this, you're not going to converge to the true value function. You're going to take essentially too big of steps, and you're going to update your value too much in the direction of what you just experienced. So all TD does is says, OK, let's not do that. Let's just move a little bit in that direction. Namely, we have some parameter alpha, and alpha here is just a number somewhere between 0 or 1. So we're going to move alpha in that direction and keep the rest 1 minus alpha, just according to our current V prime S. Sorry, this here should have read V hat S. OK, so that's just here in a little clearer writing. So our estimate for the state that we started in is equal to our old estimate of it plus alpha times effectively the new estimate of what we would get. And that's just TD. This is actually a special case called something called TD0. We're not going to talk about it today or in this class at all. But there is actually a generalization of this that looks not just at the next step, but also at, say, the reward you get 2 times from now or 3 times from now. In fact, it uses all of the rewards you experience in the future to update this guy here, because those are also estimates of the value of that state, right? So that actually leads to a class of algorithms called TD-Lambda. If you've seen that before, it's essentially a slight modification of this algorithm to take into account more rewards you see. But we're not going to, that's all I will say about that. It's really just in case you have seen that before, just know that's sort of what it is. Slight modification of this thing here. And you repeat this process just however long you want. And you may be starting with some initial value function, say initialized to all zeros. You just repeat this. You start moving a little bit in the direction of this thing. And what we have after this process is that it actually is the case that this thing here will converge to the true value function. That actually requires a few other technical conditions, like you have to decrease your step size a little bit, which we're not going to get into here. But for under kind of standard optimization type conditions, you actually will converge to the true value function here. Again, and also with the caveat is, as long as you visit all states sort of often enough, which we're not going to talk about how we do that until later. So that's TD. But there is kind of a weird problem here. And this weird problem is we've managed to learn the value function for a policy without building a model of MDP. That's great, right? We're happy about that. But what do we do with that? So we have a value function, so that's great. How does that actually help? Typically, in an MDP, you would do something like this, right? A common step in improving your policy would be to say, take the value function for your current policy, and then create a new policy which takes actions greedily with respect to that policy. So say you want to find some new policy now, which would be the max over A, sum of all s prime, t, s, a, s prime, v pi, s prime. That's how you would go about, for example, taking a greedy policy with respect to this value function. But now we're back to needing the model again. So it isn't really clear why this is even useful, right? Because how does the value function help us? Even if we estimate the optimal value function, say, and you can modify TD to actually estimate the optimal value function. It's a little tricky, but in some cases you can do that at least. But even if you have V star somehow, what would you do without a model of the system? Right? You need, I mean, going back here, this is the optimal policy. It has the model right there. Why does it help you to know the optimal value function if you can't actually take actions according to it? So, seems not that useful. Well, it turns out we can make a slight change here that does make it useful. That makes it, actually allows us to do this. And this leads to algorithms called Sarsa and Q-learning. And so to do this, to get around this problem, we're going to take a little bit of a detour and define a new type of value function called a Q function. Now, Q functions are exactly like value functions. They're just defined over both states and actions. So what I mean by that is, for a given policy, Q of S and A That is the value of taking action A in state S, and then after that, you end up at some new state S prime, and then from then on, you follow the policy. You may not follow the policy on that first step, but after that, you follow the policy. That seems weird, right? Like, why would you care about that? Why would you want to know what you did the first time? So actually, first of all, this makes sense to everyone. So this equals the reward here plus the sum of all next states, this thing, this looks so far exactly like the value function definition, plus this thing here, I should have a pi on top of it, which is the Q function for the next state times the action being the action you take from that policy in that new state. Similarly, the optimal Q function is defined as being in state, the value for being in state S, taking action A, and then from then on acting optimally. That's the value that's the optimal Q function here. And I'm writing them now both in terms of their sort of Bellman type formulas here. But really, fundamentally, these are really just the value of starting in the state, taking that action, and then acting according to the policy, or the value of starting in the state, taking that action, and then acting according to the optimal policy. Now, what's nice is that this seems odd, right? Like, well, why would we care about taking an action that's not optimal the first time if we're just going to take the optimal action thereafter? But what's interesting here is that this trick here actually allows us to get around the problem we had before. And it does it because, unlike, actually maybe I'll just write it here first. Unlike this case here, where the optimal policy defined in terms of the optimal value function equals the max over A, sum over S prime, T, S, A, S prime, B star, S prime. That's the only way you can really define the optimal policy for a optimal value function. For the optimal Q function, and you can convince yourself that this is right, because this is exactly equivalent to this expression here, but this can also be written as S equals just the max over A, Q star, S, and A. Okay, so if we know the optimal Q value function, we can compute the optimal policy without knowledge of the dynamics. And that's why people move to this weird Q notation in states and actions and all this kind of crazy stuff. It's just so you can compute policies without knowing the dynamics. Yeah? Exactly. So here, I'm just writing out the actual equations here, right? Same as the original definition of the Bellman equations. We have the model here again. What we're going to do now is define a couple of temporal difference-like methods that compute these things. They compute Q functions rather than just the value function. So that's just like TD. We're going to form a stochastic approximation to these equations using samples that, again, like TD, under proper conditions will actually converge to the true ones without knowing the model. So that's the basic idea of what we're going to do. And the reason we do it is that if we have these things, we can do the steps that we want to do without having the model anyway. All right, so here are the equations. They're kind of a little bit messy, but really it's pretty simple. So just like when TD, our process here is that we start in some state SA, we take the action A. By the way, this action does not need to be the action you generate from the policy. It could be a different action as well, but could be the policy. Doesn't have to be. Unlike TD, where the action had to be the policy because we're only evaluating the value of that one policy. So here, so observe state S, reward A, take action A somehow, chosen however we want to take it, and observe the next state S prime. There are now two algorithms which correspond to finding the value of that policy, but the Q value could expressed in terms of the Q function of that policy, or the optimal Q function. Depending on which one you want to estimate here, right? There are equations for both on the previous slide. You use either algorithm called Sarsa, which looks just like TD, except you're plugging in now, essentially, basically this estimate here is mostly the estimate as it was before, plus the reward you see, plus the Q function for the next state. So it's basically just like TD, just written in terms of state action value functions. Similarly, Q-learning is trying to estimate the optimal Q function. And that looks essentially just like a stochastic version of the equation we saw for the optimal Q function. Maybe I'll just write that down again. So optimal Q function, this equals the reward, state S plus gamma times the sum S prime T S A S prime, then max over Q, max over A prime I'll say because I already have an A there, of this optimal Q function, S prime A prime. Okay, that was our Bellman equation here for the optimal Q value function. Sort of getting harder to read that, isn't it? But oh well. Again, Q-learning, for example, is just kind of the TD-like version of that, the stochastic version of that. We don't want to, so now we just experience some state S, we take an action A, and we see then the next state S prime as well as the reward. We don't want to just fully move towards that as our update though, so what we do instead is we kind of take a little guarded step. So we have this thing here be equal to lots of just what it was before, plus alpha times this guy here, which is the reward that we saw, plus this guy here, which is just the next state that we saw, but we still have to max over A prime to get sort of the best next action we could take. So this goes to Q hat star, goes to, I'll leave out the inputs, goes to 1 minus alpha times the old Q star plus this thing. Or, I'm just leaving this out so I don't have to write too much. Okay, so again, high picture, all that's happening here is that we want to compute these things, but as was mentioned, we don't have a model of the system. The way we do that then is we just do the TD approximation, which effectively says, look at the samples that we have and make the update based on those, but don't make a full update. Make a kind of a smaller update, such that when you get enough samples, this will kind of converge to something that looks a lot like the true. In fact, again, if you pick sort of alpha properly and make it decrease in the right way, you can actually have these things converge to the true Q pi and Q star. Again, if you see this all frequently enough, and very importantly here also actually, well, actually maybe let me lay that further. These things don't always, when I say these converge, this is in this case. So if you apply other things, like we'll talk about function approximation in a second, if you apply those things, these may no longer converge. So all I'm talking about right now is essentially if you have your functions represented as an individual Q value for each possible action and each possible state. Okay, so this will converge in that case. Does not converge as sort of the general algorithm. So we'll talk about that in a second. All right, so this is kind of nice because now with Q-learning, for example, we're able to learn the optimal policy. And I should also say, of course, for both of these, you would just, you can maybe either improve the policy or with Q-learning, you just pick the optimal policy there. So for Q learning, you can actually learn the optimal policy of this MDP without a model of it, and without actually ever even building a model of it. You just form these updates as you experience things, and those somehow kind of magically converge to the estimates of the actual true optimal Q function, and therefore the optimal policy. So that seems great, right? Of course, maybe going back a second, this is the problem. It's great that they work. They don't always work that well. And furthermore, is it that great of a gain here? Because we sort of motivated this a little bit by saying, well, we don't want to just learn the MDP, because then we're just solving an MDP. These things don't really scale that well. But through all of that, through all of this at least, I'm still talking about having some representation of our Q function where we enumerate the value of every single state action pair. That's maybe a little bit better than learning the MDP. For those that are curious, right? The MDP would require the number of actions times the number of states squared terms in the transition matrix. So you have to learn this many terms to learn an MDP, whereas this would be sort of model-based. Whereas the model-free case, we still have to enumerate every single state action combination. So the model-free case, I guess, would be number of actions times the number of states. That's better, right? Certainly, maybe better. But this is sort of also a stochastic approximation now. And those things are often less efficient at using data than the other ones, as we saw in this thing. So this is a little bit more space, maybe, to store on your computer. That's sort of the advantage here. You maybe need a little less space to store it on your computer. And again, that's not a trivial concern. I mean, s squared is a lot bigger than s, but it's not. For a lot of systems, the difference here isn't going to make a huge difference. You'd rather go with the one that needs a lot fewer samples to do better. So why have RL techniques been so widely known? And why do you all know that term? If they don't really seem to, at least the model-free ones don't really seem to have that much practical use here. And the answer really comes from the case where the MDPs are too big to represent, but we don't store the Q or value function exactly. So the big element here is what's called function approximation. So remember, when we talked about, say, machine learning, you guys all classified digits, right? So a digit, we called it a vector x. We said it was, I guess, really in 0 or 1 to the 28 by 28. 28 times 28. But really, if you look at the real digits, if you actually just made those binary, it wouldn't make that much of a difference. You could still see what digit it was. So let's just talk about digits being things in 0 or 1. 0 or 1 to the 28 squared. Okay, that's a digit. Now, in machine learning, you're looking for a function that made predictions from these things, right? It took this as an input and output something else. You did not do that by enumerating every single possible assignment here. You did not do that by enumerating every single possible assignment here and tabulating what digit that was, right? All 2 to the 28 squared of these. That would require more, size and atoms in the universe or whatever those things frequently are. You didn't do it that way. So why on earth are we doing it this way here? Why are we, representing this Q function or value function or whatever by specifying the value for every single input. That seems silly. We spent all this time in AI talking about how we can get around that. This is exactly what function approximation does. So function approximation says, let's not be crazy and make these things all sort of explicit. Let's instead do what any normal machine learning person would do and approximate this thing with some function approximator. So I'm going to write that here, and I'm going to go back just for the time being, just in the simple case of value functions. You can do the same thing for Q functions, by the way. It's just a few more characters to write. So I'm going to write this now as no longer sort of some table that lists all the values of this, but it's just going to be some function parameterized by parameters theta of our state S. So for example, in digits, what we did was we actually just had a linear classifier that would just take all those digits and multiply them by something and add those all up. And that was our classifier. We could do the same thing here. We could take the states and multiply them by some parameter theta. That probably would not be the best function approximator necessarily, but we could do a lot of things, right? We could use nonlinear features. We could use neural networks. We could use any kind of f we want to approximate our value function. And it turns out, actually, TD extends directly to this case. This is really one of the big reasons why it has become so popular. I won't derive this, but essentially, the TD update looks a lot like the case before. It just basically says that your parameters are disturbed by something that looks a lot very similar to the equation we had before, times the gradient of the function with respect to those parameters. So don't worry about the precise form there. Just know that the point to know here is that TD can be extended to this case where you approximate value functions or Q functions with some function approximator. And you can do the same thing for Sarsa or Q-learning. By the way, Sarsa is a weird name. Does anyone pick up why it might be called Sarsa? It's because you see a state, an action, a reward, a state, and then the next action. So S-A-R-S-A. That's the updates it uses. Q-learning is more obvious why it's called Q-learning. So this is why people use model-free methods. You have a situation where the MDP is just too big to enumerate everything. You still want to learn a value function, but so you can't, learn the MDP and then solve it. So what you do instead is you try to learn the value function directly using TD or Q-learning or Sarsa, and then use a function approximator to represent your value function. Now, this also runs into sort of a whole host of problems here. All those nice things about convergence I talked about before, those do not apply anymore, necessarily. Sometimes they do, but usually they don't. Especially if you're acting in a way that's different from the policy you're trying to evaluate, those things almost never converge for sure. They do in practice, but they're not guaranteed to. Nonetheless, though, these things have proven effective, and this is, I think, why RL has been such a potentially great thing to do, to learn the value functions directly instead of trying to learn the MDP itself. In fact, there are a few sort of notable successes of reinforcement learning. And the sad thing here, actually, is that this is still considered a success because it happened more than 20 years ago now. But this actually was one of the big, historically, it came out right around the time that reinforcement learning was being promoted. And I think it really kind of made this into or at least not made it, but it really heavily drove forward interest in the area. So Gerald Tesaro at IBM, he developed the best backgammon player best AI backgammon player in the world using TD. He used TD with value function approximation because, of course, there are way too many states in backgammon to describe them all exactly, or to write down the MDP exactly. he actually used plain TD because backgammon is interesting in that we actually do have a model, right? We have an MDP. We just can't enumerate all the states. So if you if you have a value function, you're actually OK. Because for one next state, you can either simulate or sort of figure out what all your possible moves are for that one state, and then pick the best one. So actually, a value function is enough for this one. It's kind of a minor point. Don't worry too much about that. But essentially, TD by itself, you don't need Q-learning here. You can just use TD because you have a simulator of the environment. Yeah?
So is he using the value function in like an alpha beta kind of state tree?
I think I know there was some search built into it at some point. I believe there was actually, in the base version, though, there is no alpha beta anything. There is just TD. You just learn because right? So say you have the optimal value function. OK? The real value function. And you can't quite get it because it's, he's using neural network to approximate it. But if you have the real value function, then not just approximately, but the honest to goodness optimal action you can take is to look at all your possible actions. And for one state, there aren't that many possible actions in backgammon. There's a few, but it's still innumerable. This is just this. The max over A, sum over all S prime, T, S, A, S prime, V star, S prime. That is the genuine optimal action. There is no alpha beta pruning here. There is no search tree. There is just one thing saying, I'm going to look at the next state, see what the best value is, and pick that one. What alpha beta search does, or what any kind of game tree search does effectively, is actually estimate this thing by simulating forward. Right? It estimates what the optimal value function is by actually taking actions and sort of doing a forward search to see what, if they do the best thing and you do the best thing, et cetera. See what this thing could be. But if you have it already, you can be greedy. You can just take the action based upon that one value function, and you do great. In fact, you do optimally. So you don't need any forward search. You don't need any alpha beta pruning. You just do this. Now, oftentimes people do combine these with, say, a couple layers of alpha beta pruning, and at the last layer, you do this. It's actually kind of a nice combination of the two approaches, because to take into account for the fact that this is not actually an exact value function. But TD-Gammon, at least the standard versions, just does this. And in fact, actually, some experts in the world changed how they would play based upon strategies that TD-Gammon found. So it was really kind of a not just a good AI, it was really a world-class player. And this spawned a ton of interest in these methods. And unfortunately, for a very long time, when it came to sort of pure TD methods, this was kind of still the most impressive example. And maybe still is the most impressive example of pure TD methods, which is kind of sad, right? Because now it's been 22 years. And we still talk about this. But nonetheless, a very impressive example of TD methods. Just to highlight that this is not a dead area. This last December, a bunch of people at this conference called NIPS, which is a machine learning conference, they published a paper. They're at a company called DeepMind. They published a paper that would use Q-learning. So pure RL methods, Q-learning, to learn how to play Atari games when given just as input the pixels of the image. So not some sort of description of like what's actually going on in the game. That's pretty easy, right? If you like tell it, here's Pong, here are your actions, etc. But just the pixels, it would figure out how to play the games. Just using Q-learning. And they used a function approximator again, which was a deep neural network. So again, all this non-progress, now people are finally making progress again because we're kind of doing neural networks again, I guess. We'd have to get back to neural networks, it seems like. But that's pretty cool because it just takes these raw images, high-dimensional raw images, much like your digits, and learns how to play the games from that. Achieving, in a lot of cases, better than human play, but sometimes at least better than, but all the time is better than any other algorithm they could find, but sometimes better than human play. And as the ultimate metric of whether this kind of stuff is good or not, they were bought by Google for some ungodly sum, I think $400 million or something like that, for this little game here. So in just this January. So I should put this actually at the beginning of the course, right? Because then you might start doing this for your class project. Get bought by Google. All right, so I probably won't get to the last section. Oh, well, maybe I will. OK, let me just blaze through this now. So that was really the core of this lecture here, because reinforcement learning is sort of connected to these TD methods. These are the canonical reinforcement learning methods. There is another class of methods, though, which are called direct policy search, which go even a step beyond and say, let's not even worry about value functions. Let's just talk about learning the optimal policy, or in fact, a policy. Now, normally, you take your policy as according to maximizing your Q action functions, Q state action function, for example. But here, we're going to define, just like we defined a function approximator to define our state action value function, we could just as easily directly define the policy in terms of a state action value function. Sorry, in terms of a function approximator. Policy in terms of a function approximator, not in terms of state action value function. And this is kind of very intuitive, right? Because that's kind of simple, right? We don't worry about value functions or MDPs. We just encode what we want to do as a policy. And this is now an optimization problem, right? So find the theta, which parameterizes our policy, that maximizes the value starting, say, from some state S0. You have to put an initial state in now, because unlike in an MDP, where you can learn the optimal thing to do for every state, when you do this, now you're actually committing to sort of doing best for a given state, starting state. Or maybe it's a distribution of our starting states. That also works. But still, you want to learn parameters that maximize the sum of rewards when you start in some initial state. This is non-convex. We cannot always do this. And even when we can do it, we don't expect to find the optimal policy exactly. But furthermore, this is actually even harder than that. Because, remember, we don't have a model of the system. All we can do is generate samples from it. So we can't do things like compute gradients of this thing, analytically at least. We can't just plug in math and compute a gradient there. We need some other way of optimizing it. And there are a lot of ways of optimizing this, I should add. Here is one that works pretty well in practice. And this is the last thing I have to say about this, actually. It's really just, you can go back and refer to it if you want a little bit. But essentially, what you do is you can do a lot of things. One very surprisingly good thing to do is to take some sort of initial guess of parameters and just perturb them a little bit, say m different times. So maybe like add Gaussian noise to these parameters. Something really brain dead like that. I mean, it can be really, really simple. Just perturb it. And then execute your policy with those perturbed parameters. And compute these terms, which I'm calling j here, which is the sum of rewards you observe from that execution. I'm going to infinity here, but you could just, we're doing it discounted rewards here, so you could just trunk it after some amount of time, and you won't lose that much more. So now what we have is we have a bunch of different parameters, and correspondingly, a bunch of different sums of rewards. Now what we do is we just learn a model with machine learning or any other method that we want that maps parameters to the reward. So we learn a function approximator. I'm going to use g here because this is different from my policy function approximator. We learn some function g such that g of theta I is kind of equal to ji for all I. So that function effectively is acting like the value function for a given policy, right? So this is, for whatever policy we give it, this is kind of like the value of that policy, where the policy is specified in terms of these parameters now, directly. So instead of taking a gradient step in our original sort of true value function, which we want to optimize, we just take a gradient step in this thing. And I'm calling this actually a plus here because it's trying to optimize, we're trying to maximize our sum of rewards. This is called a first order policy search method. It goes by a lot of names actually, but it's really simple and it actually works surprisingly well. And to do better, you can do a little bit more fancy updates here. You can have fancier models there, or you could select your perturbations a little bit better. But those things are actually all kind of, they can make it a lot better, but this works pretty well. All right, so let me just show a quick video now of this happening. So this is a video from Jan Peters' group. Jan Peters is in Germany. And he does a lot of work with teaching robots to learn motor skills. He's actually the former postdoc, I think, of a person who's giving a lecture here on Friday, Stefan Schall, who's visiting CMU, is going to be lecturing on Friday. So if you want to check that out, he'll have a lot of sort of probably similar things. So basically what it's doing is you saw that first demonstration, because it wanted to first, it's trying to get this little ball into a cup here. And the human first demonstrates it, so it has sort of somewhere to start. That essentially gives it the initial theta parameters. And now what it's doing is it's adjusting the parameters based on what happens when it swings this thing to try to improve the policy. So there's some cost function, essentially, which gives it a reward of plus 1 if it gets close to the cup, and -1 if it doesn't get above the cup's line, et cetera. And eventually it's able to do that sort of very repeatably and reliably get the ball in the cup like that. So that was one example you saw, but it can do that again and again. It keeps doing that, yeah.
Is it using like vision for like to figure out?
Yeah, so I mean, there's a whole system behind it too, right? That does like the tracking of the actual ball and figuring out what happened and sort of the motion controller for the robot itself. Those are all components there, and they are important components, which we'll cover in the next several lectures actually. But the actual change time to time. Those are all the same every time, right? So the vision component stays the same. The motor controller stays the same. What changes is the actual policy that you execute, which is the sequence of controls that try to get the ball in the cup. Yeah. All right. So I'm out of time to talk about this too much, but it's in the notes, essentially, or in the slides rather. Essentially, all the problems I mentioned so far have this issue of, I kept saying, right, like for the right states and actions, as long as you see enough of the right states, as long as you see everything, you're going to be OK. And getting that right is actually really hard to do. And the fundamental trade-off here is, if we have some model of a system, say, should we try to exploit that model? Should we try to sort of do the best thing we can in that model, sort of knowing that that's going to be OK? Or should we try to explore different actions that might ultimately be better? That's a very hard problem, actually, to deal with. And in fact, here's something that does not work, would be just trying to sort of build an MDP model and reward, and then act according to the optimal policy in that model and reward function. That procedure like that can get stuck in local optima and actually can fail to do what you want to do. You can fix this, though, by just adding a little bonus on state action pairs you haven't seen very often. So if you add a term that looks like this to each state action pair, or rather to the reward function, where this is the number of times you've seen that state and that action, everything works then. But that's crazy, too, because what that's saying is try everything you haven't seen so far until you've seen it enough to form a really good estimate of it, which for most situations is not what you want to do, right, when you're learning. Maybe a little bit, don't explore too much. And this is really a big issue that still comes up a lot in practice. It only gets more troublesome when you have things like function approximation or continuous states or these other elements here. So reinforcement learning. It's MDPs where you don't know T and R, or where they're too big to actually compute MDP solutions exactly. Many different approaches: model-based, model-free, policy-based, value function-based. And finally, this is still a hard problem. The task of doing everything, of learning how to perform optimally while trying to learn the domain, while sort of being in a single chain of experience, that's a really hard problem. And we've made some progress in this in the last 20 years, but it's still very much a hard task here. So all right, we'll talk next time about vision and get to how we can track those balls.